Alright, this is lesson 7.1, exponential growth and decay. The objective for this lesson is to use exponential growth and decay functions to model real-world situations such as internet growth. So first of all, if you haven't done so yet, on the main home page for this lesson, there's a couple of YouTube videos that I would like for you to watch because I would like to discuss those. So if you haven't watched those yet, pause this video and go back to the main page of lesson 7.1 and watch the two YouTube videos. They're embedded, so you should be able to just click OK. Alright, if you have already watched those, basically the very first one, if you remember the guy dropping the ping pong ball, when he dropped one ball, it sparked the others. And so you can clearly see that one will hit maybe two others, and then those two hit more, and then so on. And in the British video, where they are actually it's in a controlled environment, and you can actually see where one ping pong ball hits two or three others, and then they create a chain reaction and hit the others. Well, that's called exponential growth, because as you can see, we're slowly growing the graph. And then all of a sudden, as we start getting 5 ping pong balls, and when they start hitting others, it's going to substantially grow, and it's going to go really, really fast. So this is what's known as exponential growth, is when our growth starts really, really slow, and then it just takes off. And you can actually go the other way, which is called exponential decay. And that's when we start off, our decay actually starts really, really slow, and then it speeds up, and then it gets to virtually zero. These graphs that you see, they look like they're hitting the x-axis. Don't hit the x-axis. They get really, really, really close, but they don't actually ever touch that axis. And that is called an asymptote, which we're going to talk about in the next slide. Same way on this one. This one is going to get really, really close to this x-axis, but it's not going to touch it. Okay? So let's go ahead and take a look at some vocabulary. And the first vocabulary is an exponential function. And so every time we've dealt with this, it's always been where we've had a number in the exponent. Well, now we're actually going to have a variable in the exponent. And when we're doing this, that b is known as the base. Okay? B is known as the base. And that axis that we approach, that we get really, really close to, but the graph does not touch, is known as the asymptote. Okay? All right. So let's go ahead and graph one of these. So if I gave you the function y equals 2 to the x power, and we wanted to graph this. So remember, anytime that we need to graph these, there's a few problems that we can use shortcuts. But even if you forget the shortcuts, you can always select values for x, plug them in, and find values for y. So we're going to start with 3, 2, 1, 0, -1, and -2. Okay? And you could keep going in both directions, but typically those are good. And if there's not a plus or a minus in there, getting around the origin is always a great number to pick. Okay? So if I take 2 to the third power, because all I'm going to do is substitute it. 2 to the third power, remember, is 2 times 2 times 2, gives me a value of 8. So I get 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. And then I plug in the 2, so I get 2 squared, and remember 2 times 2 is 4. So it ends up being 2, 1, 2, 3, 4. 2 to the first is going to give me 2. So 2, 1, 2. 2 to the 0, remember anything to the 0 power is 1. So see how you can already see the graph taking shape of how it's grown exponentially. And we always typically look at these left to right, even though we're graphing it the other direction. When I have something to the -1 power, remember all it does is it moves that that term to the bottom. So it's going to be negative and then 1/2. Okay? And then if I had 2 to the -2nd, causes it to go down, and 2 squared is going to give me 4, so 1/4. So as you can see, and the bigger number I get, it's going to get really, really close to this axis, but it is not going to touch the axis. Okay, so that's what your graph's going to look like. And then once it starts, it'll actually take off. So if I actually selected 4, it would be 432. So you can see how quickly that it's going to take off. So let's actually do a couple of examples. Okay. So the formula for an exponential growth, and if you haven't printed the note sheet yet, in the second semester of Algebra 2, this would be a great opportunity to go ahead and make sure that you've printed off those note sheets, because there's typically a lot of stuff that you're going to want to refer back to, and I would suggest maybe keeping a note sheet. So exponential growth, the formula for an exponential growth is y equals a times the quantity 1 plus r to the t power. And basically all this is going to amount to is it's going to turn out to be an equation or a formula that you need to plug some information into. So a, starting out, is known as the initial amount. It's the amount that you're starting with. Okay? R is the rate. And make sure that you need to turn it to a decimal. Okay? And in order to turn it to a decimal, let's say my rate was 25%. All you're going to do is you're going to take that 25% and move the decimal point 2 places. Okay? Another way to do it is to take 25 and divide it by 100. And it will give you 0.25. Okay? So you've got to make sure and turn it to a decimal. If you leave it as 25, your problems are not going to work out because it's going to be like 2,500%. And t is time in years. So if we give you a problem where it said 6 months, then your time in years would be 0.5. So you've got to make sure and turn all of that time to years. Okay. All right. So let's go ahead and look at an example for the problem. It says in January 1993 there were about 1,313,000 internet hosts. During the next 5 years, the number of hosts increased by 100% per year. What was the approximate number of hosts after 3 years? So when you're looking at this, remember, here's your formula, y equals a times the quantity 1 plus r to the t power. So before you even start out, it's always a good idea to go ahead and find out, what is that a? What is my initial amount? Because I've got 1,313,000, I've got 100%, and I've got 3 years. Well, remember your percent is going to be, or your rate is going to be the percent. So we're actually starting with 1,313,000. Whenever you're dealing with really large numbers like that, and I know you've commonly seen, whether you've watched the news, read the newspaper, where they'll talk about the government spent $25 million or $25.5 million. Well, all they need to do is you need to put a decimal point here and label it, okay? So 1.313 is going to be a lot easier for the calculator to calculate, okay? Your R is going to be your rate, but remember, it's 100%, and I have to move the decimal point, okay? So I'll move it 2 decimal places. So it actually ends up just 1, okay? If you divide it by 100, it's going to be 100 divided by 100. Which still gives you the 1, okay? And your t is 3 years, okay? So we're just doing 3 years. So when you do this, this is really helpful when it really comes into having a scientific calculator. There is a link on the class's webpage where you can actually link up to an online scientific calculator, and then you can input the information, okay? All right, so we're going to do y equals, a is 1.313, our initial amount, 1 plus, our r is 1, and our t is 3 years. So when you solve this, it's extremely important to make sure that if you're using a scientific calculator, you can simply type it in just as it is. 1.313 parenthesis 1 plus 1, close the parenthesis. Now, if you want a power that's great, or just the squared, then you can just simply use the squared button. If you need a power, and most of the ones that you're going to do will need a power greater than 3, or greater than 2 rather, you're going to need to use this little caret button right here. And all you do is you just push it, and then push whatever power you want, okay? Now, if you have a scientific calculator, easiest way to tell if it's a scientific calculator is it has sine, cosine, and tangent on it. Okay, it doesn't have to be like this. You can get nice ones at Walmart for about $15 are the really nice ones. They've got some that are as cheap as $10. If you're having trouble using your scientific calculator, make sure and give me a call because depending on the type of calculator will depend upon the order in which you have to enter things. Okay, and there is a lot of things in this semester of Algebra 2 that you're going to use the scientific calculator. So once you've entered all of this into the calculator, though, press enter, and you're done. And you find out that over the 3 years, our answer is 10.504 million users. Okay, over the next 3 years. Okay, so let's take a look at another example. Example number 4. So if you could, go ahead and pause the video at this time, and let's go ahead and see if you can do this one. When you're finished, go ahead and restart the video. All right, so let's go ahead and check this out. So just like before, we need to make sure and get all of our variables. So we need to know what A represents, R represents, and T represents. So the problem is in 1992, when Mr. Arthur entered college, the cost of tuition at a state university was $4,650. During the next 8 years, the tuition rose by 4% each year. If this trend continues, what is the cost of tuition for students entering this fall? So we basically got 3 numbers right here. Okay. Now this is where it's going to get tricky because the question is, what is the tuition cost for students entering this fall? Okay. So a lot of times you're not actually going to have a problem that tells you the actual years because the years are actually going to change. Do not use, this is going to be really important because you know this fall, the year is 2012. So first of all, let's start off, and we'll talk about time in just a second, but let's go ahead and start off and find out what our A is. And your A should have been 4,650. Your T was, or I'm sorry, your R was 4%. If you move the decimal point 2 places, you have to add a 0, so you get 0.04. Or remember the other method is to take 4 divided by 100, and you should get 0.04. Okay. Now, if you use 2012 as your time, that's a number. It's like naming a year. It doesn't tell you how many years, it just tells you the year. So what you actually have to do is, on this one, you have to take 2012 minus the 1992, and you get 20 years. Okay? Then you can plug it in your formula. Y equals 4,650, 1 plus 0.04, and your T is 20. Okay? So if we go back to our calculator, we get 4650 parenthesis 1 plus 0.04, close the parenthesis, and this time we're going to raise it to the 20th power. Okay? And if these numbers, your calculator is going to do a decent job of solving this, and you find out that it's actually $10,188 and 72 cents. Okay, and I do expect it to go 2 decimal places. Okay. All right. So the next topic is, okay, we've talked about exponential growth, but what happens when things actually go down in value? And when things actually go down in value, it's an exponential decay, and the only difference in the formula is it's a minus. Okay, the A, the R, and the T represent everything is exactly the same. Those don't change. A is still the initial amount, R is still the rate as a decimal, and T is still time in years. Okay? All right, so let's go ahead and take a look at an example. Now you're going to have to start looking for keywords. Increased, went up. For example, in this example, it says you buy a new car for $24,000. The value of the car decreases because now we're going to mix these problems up. So now it decreases by 16% each year. What's the value of the car at the end of 5 years? So I've got 24,000, 16%, and I've got 5 years. So again, my A, R, and T are exactly the same. Those have not changed. So A is 24,000. R is 16%, but remember I have to move the decimal point, so it's 0.16. And T is 5 years. So just like exponential growth, we're going to plug it in. 24,000. 1 minus 0.16. So this minus here is the only difference. Everything else remains exactly the same. And when you enter it in the calculator, 24,000, 1 minus 0.16 to the 5th power. Okay, so the only difference is this minus sign right here. Press and enter, and you find out that your $24,000 car after 5 years is worth $10,037.09. Okay? All right, so the last problem is a U-try. Okay? So go ahead and pause the video and go ahead and see if you can solve this one. Okay, so the problem is there are 40,000 homes in Indianapolis. Each year, 10% of the homes are expected to disconnect from their septic systems and connect to the public sewer system. Approximately how many homes will still not be connected after 8 years? So, same thing. You're looking for that word, are we growing, are we decreasing? Okay? So we're trying to, and this is not a common one, but we're disconnecting, so the number is going to decrease. So anytime you see a decrease go down, it's going to tell you what sign that you actually need to use. And in this case, it's going to be the minus. Okay? All right. So our A, we have 40,000, 10%, and we've got 8 years. So 40,000 is our initial amount. R is 10%. Remember, we got to move the decimal point. And T is 8 years. Okay? So plug it in our formula. We get 40,000. 1 minus 0.10, and T is 8. Okay? So then again, come to your scientific calculator. 40,000, parenthesis, 1 minus 0.10, close, and then raise it to the 8th power. And you find out that after 8 years, there's still going to be 17,218 people connected to the public sewer system. Okay? All right. Well, this concludes lesson 7.1. I suggest doing some of the practice problems that are attached on exponential growth and exponential decay. Make sure you check your problems and complete the quick check. Thank you.